Hello everyone. In this module, we can discuss the concept of mutual information, which is generally represented with a variable I of x comma y. Mutual information is generally represented as either I of x comma y or I of y comma x also. I of x comma y represents the amount of information transmitted from x to y, that is transmitter section to the receiver, and I of y by x is the acknowledgement received from the receiver to the transmitter. So generally here we are focusing first on I of xy, which is the difference between the uncertainties due to the priori and posteriori probabilities of the transmitter section, where P of xj represents the transmitter priori probability and P of xj by yk represents the transmitter posteriori probability knowing yk. So this is a conditional probability. So P of xj, this is also the probability of xj knowing the receiver. But first one is the probability of transmitter itself. Now we are going to define I of xj comma yk. That is mutual information of transmitter events consisting of j events ranging from 1 to m and receiver events consisting of k from 1 to n, which is represented as I of xj minus I of xj by yk, where I of xj is proportional to its uncertainty and the expression for the information is minus log p of xj base 2. This is what we studied in the concept of information. Similarly, I of xj by yk is expressed as minus log p of xj by yk base 2. Now, what is I of xj comma yk? Difference between the uncertainties of priori and posteriori probabilities. So I can write I of xj comma yk as minus log p of xj minus of minus. So it will be plus log p of xj by yk. This is in the form of minus log a plus log b. So we can write it as I of xj comma yk as log b by a, where b is p of xj by yk and a is p of xj. So this is about the mutual information of transmitter with respect to the receiver. Coming to the properties of mutual information always obeys the symmetrical property. That is, I of xj comma yk is equal to I of yk comma xj. The amount of information sent from transmitter to the receiver is equivalent to the amount of acknowledgement received from the receiver section to the transmitter. So in order to prove this symmetrical property, take the LHS, that is I of xj comma yk, which is equal to log p of xj by yk by p of xj base 2. From Bayes' theorem, we know that p of xj by yk can be written as joint probability divided by p of yk. Let us replace p of xj by yk as p of xj comma yk by p of xj. Just rearranging this upon substitution, you can also take p of xj by y comma yk by p of yk. This term we can replace it as consider the Bayes theorem with respect to p of yk by xj. So we can write p of xj comma yk by p of yk. So we can write this as sorry. Actually here log p of xj by yk, we have rewritten this as log p of xj by yk, which we have replaced it as p of xj comma yk divided by p of yk. And now leave this p of yk and consider this part, that is p of xj comma yk by p of xj. So we can write this as p of yk by xj divided by p of yk. So this is in the form of log b by a, which we can write it as minus log a minus of minus, that is plus log b. So it is equal to I of yk minus I of yk by xj. So from this we can prove that the mutual information obeys the symmetrical property, stating that I of xj comma yk is equal to I of yk comma xj. And coming to the second property of mutual information, if yk is equal to xj, that is if the transmitter events and receiver events are same, then mutual information acts as a self-information. Let us take the expression for I of xj comma yk, which is equal to log p of xj by yk by p of xj. Again, rewrite it as log minus log a plus log p, that is minus log p of xj base 2 plus log p of xj by yk. But here if you observe this factor, if when xj is equal to yk or yk is equal to xj, it becomes log 1. Log 1 is 0. So directly I of xj comma yk becomes minus log p of xj base 2, which is nothing but I of xj. That is the self-information of the transmitter. Similarly, if you consider I of yk comma xj, and if you replace xj as yk, then you will get the self-information of the receiver. So whenever yk is equal to xj, mutual information acts as a self-information. This is the second property of mutual information. And let us consider the third property as average of mutual information, which is represented as capital I of x comma y, which is the average of considering all the variables that range from j is equal to 1 to m and k is equal to 1 to n. So it is equal to I of xj comma yk and consider its average. So summation j series and k series p of xj comma yk. We are considering the with respect to its property into I of xj comma yk. So you can write I of xj comma yk from the property 1 as p of xj by yk by p of xj. So split this log b by a into minus log a plus log b. So once you split that, in the first term you have inside the logarithm you have p of xj. So you can replace the outside term as p of xj. Then you can write it as h of x. So minus summation j is equal to 1 to m. The summation k is equal to 1 p of xj comma yk can be absorbed. If you observe yk elements, you will get p of xj. So minus summation j is equal to 1 to m, p of xj log p of xj is nothing but our marginal entropy of the transmitter. Minus, here you have plus sign. So minus of minus you can write. So minus summation j is equal to 1 to m, k is equal to 1 to n, p of xj comma yk log p of xj by yk base 2. This is nothing but the conditional entropy of transmitter knowing the receiver. So h of x by y. So finally we have stated that average of mutual information is equal to either h of x minus h of x by y. And similarly, from the Bayes theorem, we proved that h of xy, that is the joint entropy, is equal to h of y plus h of x by y or h of x plus h of y by x. So here you have h of x by y. The equation 1 is with respect to h of x by y. So you can replace this h of x by y as h of xy minus h of y. Upon replacing that, this minus of minus becomes plus. So h of x plus h of y minus h of xy. So here in equation 4, we have represented the mutual information in terms of two marginal entropies and joint entropy. In equation 1, we have represented it in the form of marginal entropy of transmitter and conditional entropy of x knowing the receiver. Similarly, you can also write the expression in terms of conditional entropy of receiver knowing the transmitter. So just we know h of xy is equal to h of x plus h of y by x. Just substitute h of x by xy as a h of x plus h of y by x so that you can get the expression in the form of h of y by x also. That is I of xy is equal to h of x plus h of y minus h of xy. We have written this as h of x plus h of y by x. Here h of x gets cancelled and you will obtain h of y minus h of y by x. So these are the 5 relations which interrelate the different types of marginal entropies, conditional entropies, and joint entropy. Similarly, these 5 entropies are related with the mutual information. This we discussed in the previous slides. And fourth property of mutual information is for a noise-free channel, mutual information is equal to either h of x or h of phi. We know that for a noise-free channel, there is no error. That is, if a data is transmitted from x1, it will reach to the respective destination y1. Similarly, x2 will reach only y2. xm information will reach to the destination of ym. Therefore, the joint probability matrix can be written as consisting of elements only x1, y1, x2, y2, so on, xn, ym. So you have only diagonal elements where matrix size is m by m. So P of x by y or P of y by x. The matrix is said to be P of x by y when the sum of all the elements present in individual columns is equal to 1. Then you can say that the matrix is P of x by y. In the example, if you see first column elements sum, it is equal to 1. Similarly, second column element sum is also 1. Similarly, last all column element sum is 1. So you can say that the matrix is P of x by y. Similarly, a matrix is said to be P of y by x when the sum of all the elements along the row is 1. So if you consider the first row, the sum is 1. Similarly, second row, sum is 1. Like that last row, sum is 1. So you can also define this as P of phi by x. Once P of x by y and P of phi by x is a unity diagonal matrix, our respective entropies becomes 0 because log 1 will be 0 and log 0 is also 0. But from the definition of mutual information, I of xy is either h of x minus h of x by y or h of y minus h of y by x. Therefore, you can represent for a noise-free channel, I of xy is equal to either h of x or h of x by y because h of x by y and h of y by x are 0. Therefore, for a noise-free channel where output is exactly equal to input, the mutual information I of xy is equal to either the marginal entropy of the transmitter or the marginal entropy of the receiver. Coming to the last property of mutual information of an independent channel is 0. So here in the example, you can see the independent channel P of xj comma yk, which is represented as, here in the matrix, you can see that all the row elements are equal. Similarly, even if all the column elements are equal, it is also called as independent channel. So it means that the information from x1 receives y1, y2, y3, so on, ym with equal probability. Similarly, there is also another case that the amount of information received by y1 from x1, x2, x3 up to so on xm is of same probability. That is either the row elements or the column elements are equal. But in this case, the row elements are equal. And similarly, for an independent elements, the joint probability is a product of individual probabilities. That is, P of xj comma yk is equal to P of xj into yk. But we know that from Bayes' theorem, P of xj comma yk is equal to either P of xj into P of yk by xj or P of yk into P of xj by yk. So upon substituting this independent channel joint probability as P of xj into P of yk, let us take this first term, that is P of yk into P of xj by yk. Then P of yk, upon substituting this as P of xj into P of yk, in the first term P of yk gets cancelled. Once P of yk cancelled, P of xj by yk is equal to P of xj. That is, posterior probability of transmitter is equal to the priori probability of the transmitter. Similarly, if you assume the second term, P of xj gets cancelled. Therefore, the posterior probability of receiver and priori probability of receiver is equal. Let us consider this as equation 2. But our conditional entropy H of xy is minus summation series of j and k P of xj comma yk log P of xj by yk base 2. But in the earlier slide, you have seen that P of xj by yk. is equal to P of Xj. It is equal to P of Xj. So let us write this as log P of Xj base 2. And here if you consider summation k is equal to 1 to n P of Xj comma Yk, this can be written as P of Xj. If you observe k elements, it will be P of Xj. So you can write it as P of Xj. So minus summation j is equal to 1 to m P of Xj log P of Xj base 2 is nothing but our h of x. So from the definition of mutual information, I of x by, it is equal to either h of x minus h of x by y or h of y minus h of y by x. If you consider it as h of x minus h of x by y, from the above equation, h of x by y is equal to h of x. So if you replace this as h of x, both gets cancelled and the mutual information becomes 0. Therefore, for an independent channel, mutual information is 0. So in this module, we have discussed the concepts of mutual information as well as its properties. In the next module, we can discuss the two different types of encoding techniques, Shannon-Fano and Huffman coding methods.